Hi, so in this video, we're going to take a look at TCP slow start. So let's get started. So here we have PCB once again sending its receive window to PCA, saying, don't send me any more than 64,000 bytes of data without receiving an acknowledgement from me. So PCA says, okay, I'll create a send window when I send data for sending data to you using your receive window that you sent me and my congestion window that we talked about previously. But I need to use slow start. Okay. First of all, that send window, again, it's the minimum between the congestion window and the receive window. The receive window is advertised by PCB. The congestion window is determined by PCA. We're going to begin to see how that's done here in a moment. Okay. Now remember, the send window is the lesser window size between that receive window and the congestion window. So we're going to see here in a moment that our congestion window is going to start at about 14,600 bytes. TCP slow start. It's a congestion control mechanism that begins with a small congestion window and increases exponentially with each acknowledgement received, in this case from PCB, allowing the sender, PCA, to gradually probe the network's capacity without overwhelming it. As segments are sent and acknowledgements are received, the congestion window increases and the send window also increases. So we begin to see how this all happens. Okay? So once again, as segments are sent by PCA and acknowledgements are received from PCB, PCA will increase its congestion window and therefore also gradually increasing its send window. Okay, so we said PCA is going to create a send window using the receive window from PCB and a congestion window that it determines. And again, it's the minimum of the two. TCP slow start and the congestion window. Again, the congestion window starts with a small size and increases gradually until packet loss is detected or a threshold is reached. So slow start and congestion avoidance phases. Talk a little bit about that in a later video. The congestion window increases gradually after each acknowledgement received from the receiver of the segments, PCB, who's sending those acknowledgements. At the beginning of the transmission, the send window will be small, equal to that of the congestion window. Okay, if there's no congestion on the network, the congestion window will continue to increase. Ultimately, the receive window and the congestion window will be equal. And the send window will be whatever transmission rate the receiver PCB can handle. That will be its receive window. So we'll see this in a moment. We'll see where this congestion window increases to where it's equal to that of the receive window, and that's where the send window will be maximized at. Okay, time for a little example. Okay, so again, TCP slow start is used initially to gradually increase the transmission rate and avoid overwhelming the network, helping to prevent congestion by starting with a small amount of data and increasing it as the congestion proves stable. Okay, and in this example here, we're gonna assume no congestion on the network. Later, that's in a later video. We'll take a look at that. Okay, so the congestion window, what does it start at? The recommended initial congestion window should be set at 10 segments. That was a later enhancement to TCP. At one time it was 1 and even just 2 segments, but now it's 10 segments. What does that mean? Well, the initial congestion window should be 10 times the maximum segment size, TCP maximum segment size. In a previous video, we saw that the typical TCP maximum segment size is 1,460 bytes. So 10 times that is 14,600 bytes. So our send window is going to be the minimum between our congestion window and receive window. Okay, this means it's going to be the minimum between the right now congestion window of 14,600 bytes and the receive window that PCB is advertising of 64,000 bytes. So the minimum of that, well, that's the 14,600 is the lesser of the two values. So PCA goes, okay, my send window for this first segment until I, calculate differently is 14,600 bytes. Since we are just getting started, I don't want to overwhelm the network. All right, so the congestion window set to that small value, 10 maximum segment sizes. Yep. So we saw that was 14,600 bytes is the initial congestion window, which right now is the send window. It's less than the receive window. Okay. So this tells PCA that my send window is 14,600 bytes. Okay. Every time I get an acknowledgement for two segments that I sent. So if I send two segments and I receive an acknowledgement, you know what? That tells me a little something. That tells me that there's no congestion on the network. So I'm going to increase my congestion window by 2 more maximum segment sizes, or 2 times 1,460. Okay. So PCA sends a couple of segments. Let's see what happens. Okay. So PCA sends 2 segments. It just received an acknowledgement for those 2 that PCB says, I got those segments. As the sender, PCA transmits data. The congestion window increases based on the number of acknowledgements received from PCB. So it just sent the first 2 segments, received an acknowledgement. Okay, so this is where PCA actually increases its congestion window. It's going to increase exponentially. Okay, it's going to increase by 2 maximum segment sizes, 1 for each segment that it sends. Okay, let's see. My initial congestion window was 10 maximum segment sizes, 14,600 bytes. I sent 2 segments that you acknowledged, each of 1,460 bytes. So I'm going to increase my congestion window from 14,600 to 2,920. The 2 maximum segment sizes that are the acknowledgement for the 2 segments that I sent you, each of 1,460 bytes. Okay, I think you're following this. So it's increased 2 segment sizes. So now we're at the congestion windows at 17,520 bytes. So what's the send window now? It's the minimum of the congestion window, 17,520, and the receive window, which is currently still 64,000 bytes. So the send window is, of course, going to be the minimum of these, which is 17,520 bytes. So PCA says, oh, my send window is now 17,520 bytes. The effective send window will always be the lesser of these 2 values. Now, keep in mind that PCA is continuing to send segments to PCB. It's not waiting on these acknowledgements. Remember, we're using sliding windows, and also remember that this send window, whatever it was before, 14,600, now 17,520, it still hasn't reached that window size. Okay, it hasn't reached at the end of that last byte. So it's continuing to send. There are bytes still in flight from PCA to PCB while PCB is sending this acknowledgement. Okay, so let's take a look at some more examples here of what's going on. The receive window's 64,000 bytes. Okay, we saw our congestion window was initially at 10 maximum segment sizes. So we sent those 2 segments. Let's just see this again. We got that acknowledgement. So it was 14,600. We're just going to now increase it by 2. Okay. All right. We're going to increase it by 2. adding 2,920. This actually here should, let's see, now get rid of that there. Okay, it's really just 14,600 bytes. Here we're increasing it by 2 maximum segment sizes. Okay, so delete that from your mind there. Okay. So now our send window is 17,520 bytes. PCA continues to send segments, PCB, no congestion here. So continues to send acknowledgments for every 2 segments. Again, now PCA says, oh, I just received another 2 acknowledgments. So I'm going to increase my send window, another 2,920 bytes, another 2 maximum segment sizes. So I'm going from 17,520. Now I'm at 20,440. And I just keep on sending these segments. Okay. And again, using sliding windows, PCB sends it acts every 2 segments, allowing PCA to continuously increase its congestion window by 2 maximum segment sizes and transmit more data. So we've got this nice synchronous flow happening between the two. Okay. This continuous flow of acts ensures that the effective send window defined by the minimum of the congestion receive window is not impacting transmission, because right now there is no congestion. Okay, so as a result, we can see that taking advantage of the available bandwidth and maintaining a steady transmission rate, keeping the data flow smooth and uninterrupted. Yep. And again, notice that the congestion window is continuously increasing, which means the send window is continuously increasing. But as long as PCA hasn't reached that last byte, it's sending that segments in flight while it's waiting for acknowledgement. So there's no stop and wait happening here. So again, the key to this is if the maximum segment size is 1,460 bytes and delayed acts are used, that means where the receiver sends an acknowledgement for every 2 segments, the congestion window will increase by 2 maximum segment size, in this case, 2,920 bytes for each act received, each acknowledgement received. Okay. At some point, the congestion window will be greater than the advertised receive window, right? If we keep on going at this pace. Okay, so let's see. We've just sent another couple of segments here. Our receive window is at 64,000 bytes. Our congestion window, let's say right now is adding another 2,920 bytes. Another 2 maximum segment sizes. Our send window is now at 46,720. Send another 2 segments, receive an ACK. Okay, continuing to increase that congestion window, which also increases our send window by 2,920 bytes. We just keep on going. Okay. All right. So still, the congestion window is less than the receive window. Okay, we're at 52,560 bytes. Let's keep on going. All right, now we're getting close. Our congestion window is now, by increasing it another 2,920 bytes, that's 61,320 bytes. Getting close to that threshold, what the receive window is. So our send window is getting close. Okay, send another couple of segments. Now we get an acknowledgement. Now look, our congestion window has now gone above our receive window, 65,720 bytes. So remember that it's not only our send window is going to be the lesser of the 2 values. So instead of increasing the 2 maximum segment sizes, it's going a little less because we got to keep it under the minimum between the congestion window and the receive window. The receive window is now the minimum of these 2 values. Okay, remember, that's what our send window is, the minimum of the congestion window and the receive window. All this time, the congestion window has been less. Now the receive window is less. Okay, so now our send window is now going to be equal to the receive window of PCB. And that's really what we want, right? We want it, as long as the network can handle it, we want to go maximum whatever the network can handle. Okay. And the limitation now is coming from the receiver of these segments, PCB. And that's what we want. So also note that PCB includes its receive window in every TCP segment to PCA. And this value can increase or decrease at any time. So right now, we've just kind of kept things simple and shown that the PCB has kept its receive window consistent or constant at 64,000 bytes. Okay. But I hope you can see here that our send window starting off small, okay, at 10 maximum segment sizes, 14,000, which was 1,460 bytes times 10, 14,600 bytes, and gradually increased until it reached the receive window of PCB, in this case, 64,000 bytes. So eventually we are where the congestion window is maximized and greater than or equal to the receive window. So our congestion window, now that it's equal to or less than the receive window, our send window is now maximized at 64,000 bytes. Okay. PCA can continue to send data into the network at the highest rate that PCB can handle. And again, this assumes that the network is experiencing no congestion or other issues and can handle this transfer rate. Okay. And again, PCB may change its receive window based on what it's experiencing or its buffer. Talk about that a little later. I do want to mention that TCP Slow Start has undergone several improvements over the years to enhance its performance and efficiency, especially in today's modern high-speed and data center networks. Here are some of these that you may want to take a look at, like Cubic, BBR. I love this, bottleneck bandwidth and round-trip propagation time. Wow, glad they call it BBR. Another big change that's been happening the last several years with TCP is how to make TCP more efficient in our data centers. So we have TCP, data center TCP and TCP Vegas, which was prior improvements on TCP Tahoe and Reno. If you're wondering how they come up with those names, this is a traditional way of naming changes, features in TCP based on, if I remember correctly, UC Berkeley in collaboration with the University of Nevada. So where a lot of this research has been done over the years. So that's why you hear things like Tahoe, Reno, Vegas. All right. Anyway, there's some other improvements that you may want to take a look at as well. But hopefully that this gives you a foundation, some of the fundamentals of what TCP Slow Start is all about. Next, we're going to look at some congestion control with TCP, how it handles things, and including later things like packet loss, duplicate acts, explicit congestion notification, and increased round trip time. Okay, but really, we've hit some of the more difficult concepts to sometimes understand that first time out. Now things become, I think, a little bit more able to handle now that we have all this understanding of congestion window, receive window, and a little bit about slow start. Hope you're finding these videos helpful. Thanks.